Hi, my name's Dr. Peter Kay, and this is the next lecture in series on automotive engineering and the internal combustion engine. If you have any comments, queries or questions about any of the material in this lecture, then please email me or come and see me. My contact details are there. So this is week 3, combustion. If you missed any of the other two on ideal engine cycles or engine geometry, probably a good idea to go back and watch those first. But as I say, this one's on combustion, the chemistry of combustion. So the contents of this lecture, I'm first going to talk about fuels in a kind of general sense and what gasoline and diesel are made up of. Then I'm going to talk about the chemistry of combustion. So what's actually happening? We know that we put air and fuel into an engine and they combust to give us energy, but what's really happening? I then talk about stoichiometry. So this is kind of the ideal amount of fuel to air that you need to promote the best and cleanest combustion. However, we do get emissions produced. I'll talk about that, which pollutants are produced and where they come from and why they're bad for us. And finally, I'll finish off by talking about emission standards, because we obviously want to control those, and how we can treat the engines to remove some of the pollutants. So first of all, I'm just going to talk about fuels. So the table below shows the specific energy. Now the specific energy is the energy per unit mass, and energy density, which is the energy per unit volume of a range of fuels. And you can see from the table there that gasoline and diesel are relatively similar in terms of both energy and specific energy and energy density. And if you compare them to some of the others, I'm just going to highlight hydrogen here. This is a good example to compare it to. So on the face of it, in terms of specific energy, hydrogen looks like a much better fuel because you get nearly 3 times as much energy per unit mass. But the problem is that because hydrogen is a gas at room temperature, you don't get very much energy per unit volume. So you need a lot of it to kind of get that energy, even though it does give you a lot per unit mass. So this is why these fuels are, pretty good, because they give you a lot of energy for a small volume. So if you're carrying that volume of fuel with you, then that's ideal. Comparing it to some of the others, ethanol is down compared to the gasoline and diesel. Also battery technologies, you can see nowhere near the kind of liquid fuels. Perhaps not a fair comparison because they do work in fundamentally different ways, but nevertheless I thought I'd put up there for interest. And finally you can see, again, not very good direct comparison, but this is why nuclear power is so good. So as I said, gasoline and diesel kind of compare well to some of the other fuels that I've listed there. And just for comparison, the most efficient solar panels produce around 175 watts per meter squared. I've put that separately because you can't really convert that into a kind of a mass or a volume, but it's just for comparison. Anyway, it doesn't bear too well when you compare it against the liquid fuels. So the majority of fuels that are burnt in engines are made up of hydrocarbons, and hydrocarbon, as the main name suggests, is a molecule that contains hydrogen and carbon. And alkanes are the simplest form of hydrocarbons. So there's a couple up here shown graphically. So they're very simple, that they have single bonds between them, so it's just a carbon chain with single bonds with hydrogens branching off each of the carbons. The simplest hydrocarbon that can occur is methane, which is one carbon with 4 hydrogens. This is a gas at room temperature because it has a very low boiling point, and it's the main constituent of natural gas. As you start increasing the number of carbons in the chain, you start to move from gases through ethane, which is used in polythene, propane, which is used as a camping gas, and in blowtorches, butane is also used as a camping gas. To eventually we get to some of the heavier hydrocarbons, such as isooctane, octane, which has 8 carbons in it. Now I've singled this one out because octane is the kind of all the alkanes, octane is the closest approximation for gasoline in terms of boiling point and density, etc. So gasoline isn't always made up of octane, but it's the closest one in terms of its properties. And likewise for dodecane, that's the closest approximation for diesel fuel. So I just want to put this one in. We are talking about combustion, and once you get your fuel into the engine, there's what's really kind of promoting how the fuel combusts with the air is what's called the 3 T's of combustions. So if you have these 3 T's, then you have hopefully have complete and efficient combustion, and they are time. So you need sufficient time for the chemical reaction to occur. So this is sometimes known as residence time. So to put this in the context of an engine, if you've got a very high RPM, the time for combustion is finite. It needs to occur. So you want to be careful that you have time for that combustion to occur before you're discharging the reactants as in the exhaust stroke. So that's important. The second one is temperature. You need sufficient temperature to heat the fuel through decomposition to ignition, and also to sustain combustion. So in a spark ignition engine, the temperature is obviously initiated by a spark plug, and in a compression ignition engine, as we discussed last time, it's through the heat in the air as the charge is compressed. So, and it's not just the temperature to initiate combustion, but as I say, to sustain combustion as well. And finally, the last one is turbulence. So you need sufficient turbulence to mix the oxygen and fuel completely. And this is particularly important in terms of emissions control, and this will become clearer as we move through the lecture. But just think of it in kind of practical terms. You can't have all your fuel at one end and all your air at the other end. You want it all nice, homogeneously mixed to get the best combustion. However, turbulence does cause pressure drops, which equals pressure losses, which is going to give you a penalty in terms of efficiency. But it is important. So those are the 3 T's of combustion. So now I'm going to move on to the chemistry of combustion. So if we take hydrocarbons, as I showed a few slides back, and we mix it with oxygen, then we get carbon dioxide and water. And what you're really saying in this chemical formula is the energy bonding it together here is released as it's converted into carbon dioxide and water. So what you should really say here is hydrocarbon plus oxygen equals carbon dioxide plus water plus heat, because heat is actually released from the reaction. That's why we're doing it, to release the heat, to heat the gas, to generate work. So let's start off with a simple formula. So we're going to use methane for an example. So we got CH4, methane plus oxygen, which goes round as 2 oxygens in a pair, O2, and that gives us carbon dioxide, CO2, and water, which is H2O. Now, it's important to balance the chemical equations. Now, is this equation balanced? So the answer is no, because we need the same number of carbons and hydrogens and oxygens on one side of the equation as we do on the other. Think of it in terms of a set of scales. If I put all the carbons and hydrogens and oxygens on this side in terms of the reactants, and I put all the carbons and hydrogen and oxygens in terms of the products on this side, would it be balanced? Would they weigh the same? So I'm going to show you a way that you can balance this, and this is the way that I propose. Start off, so always have just 1 unit of your fuel, and what we're going to do is we're going to mix that, we're going to burn that with X, we don't know how many yet, but X lots of oxygen, and that's going to give us some, we don't know how many carbon dioxide, so let's say Y, and some waters, we don't know how many, let's say Z. So 1 unit of methane plus XO2 is going to give us YCO2 plus ZH2O. Now, this is the way that I propose you do it, and I've been using this for years and it seems to work pretty well. Draw this little table. So put all your reactants on this side and all your products on this side, and then list down what you've got. So you've got carbon, hydrogen, oxygen, carbon, hydrogen, oxygen. Now we can already fill in 2 of the cells on this table. So we have 1 carbon in the methane, none in here, so we can put 1 in here. We have 4 hydrogens in the methane, none in the oxygen, so we can put 4 here. Now we don't know how many oxygens we've got here, so instead of putting a number, I'm going to put a formula. So we've got 2x oxygens on the left hand side, yeah, 2x. Let's do the same for the product side. So on the right hand side we have Y carbons, we have 2Z hydrogens. Okay, now how many oxygens do we have? We have some in carbon dioxide and some in water. So we have 2 in the carbon dioxide and 1 in the water. So algebraically, the number of oxygens that we have on this side is 2Y plus Z. So put in your reactants, your products, put it in algebraically. Now we can start solving for this. We know that we have 1 carbon on this side, so Y has to equal 1. We have 4 hydrogens on this side, and 4 hydrogens is equal to 2Z, so we know that Z is equal to 2. Because we now know Y and Z, we can work this one out. So 2Y plus Z is 2 times 1 plus 2, which is 4. So you have 4 oxygens. So now we can backfill onto this side. We know that the 2 oxygens here has to equal 4, so therefore X equals 2. So now we can write that in terms of our formula. So if you put it back up here, so we say that 1 methane plus 2 oxygens gives us 1 carbon dioxide and 2 waters. And now that's balanced. That's a balanced equation. So this is the balanced equation that we got from the last slide. But the issue here is we don't burn our fuels in pure oxygen. Rather, we burn it in the oxygen that's present in air. And air is made up of 21% oxygen and 70% nitrogen. So we're only 1/5 of the atmosphere we can really burn. There are other things in the atmosphere, such as CO2 and some of the other noble gases, but they're negligible compared to the amount of oxygen and nitrogen. So you might see, so if you just work with 21 and 79%, that is fine for these calculations. So therefore, we're not burning impure oxygen. So if we say that 1 unit of air has 0.21 units of oxygen and 0.79 units of nitrogen, or we can say that if we divide through by 0.21, that 1 over that, we so basically saying 5 units of air has 1 mole of oxygen and 79 over 21 units of nitrogen. Now you might see here that I've used the word mole rather than unit. In chemistry we talk about moles. Mole is just it's a unit. It's basically the number of atoms, and so it please don't be confused by it. It's just a unit. So don't think of it in terms of mole. You're just saying there are this number. It's the same. You could divide 3 by moles and take these out. But in chemistry, you do refer to moles. So therefore, for each mole of oxygen, we have, if you just work this fraction out, approximately 3.76 moles of nitrogen that carry around with us. So therefore, when we wrote our equation for methane at the top of the slide here, we really had this nitrogen going around with it. So what we had is 1 methane plus 2 lots of oxygen, but with that oxygen we've got about 3 and a bit, nearly 4 units of nitrogen. That gives us CO2 and H2O. The nitrogen doesn't react. Well, it shouldn't do. We'll talk about that later. But this should go through as an inert gas. So on this side we have 2 times this fraction of nitrogen as well. Okay, so again I've copied that over from the previous slide. So what we want to know, bringing this back to an engine, what do we actually want to know? So just say we're burning methane in this engine for this example. So we have 1 unit of methane, which is made up of 1 carbon and 4 hydrogens, and to do that we need 2 units of oxygen and nitrogen, basically 5 units of air. So how do we convert from moles, number of atoms, into mass? Because this isn't very useful. We can't count the number of atoms that's going into our car. So what we do is we substitute, or we times through by the molecular weights. So carbon, 1 mole of carbon weighs 12 grams. Hydrogen is 1 grams per mole, oxygen 16 grams per mole, and nitrogen is 14 grams per mole. Now you can get all these numbers off the periodic tables, and what these really are is they're not really they're the atomic weights of each atom. So this isn't N2, this is just N, nitrogen, and likewise for oxygen. So when we work out the fuel to air ratio, so just forget the products for instance for the time being. So we're just looking purely at our reactants. So we've got 1 unit of methane reacting with 2 lots of oxygen and this fraction of nitrogen. So we got our fuel to air ratio is this. Now we're going to start substituting in these atomic weights. So on the left hand side we have 1 carbon, and so 1 times 12 plus 4 hydrogens, 4 times 1, and that gives us 2. We've got 2 lots of this, so O2, so it's 2 times 16 plus this fraction times, you've got 2 nitrogens, 2 times 14, and if you work that out you get to a ratio of 16 to 274. Dividing 3 by 16 gives us approximately 1 to 17. So what we're saying there is by mass, this is by mass, remember, not by volume, we need 17 say kilograms of air per kilogram of fuel. And try it. Show that using this method, show that for octane the air to fuel ratio is approximately 15. So you can get the molecular formula for octane from the first slide. But anyway, as I say, the molecular weight for octane is about 15. Okay, so what we're saying is the stoichiometric air to ratio for gasoline and diesel are. So for octane, as I said, it's around 15, dodecane it's just under. But when you work it out for gasoline, it is different to what you get for octane, and likewise diesel is different to dodecane. Now what can be causing these differences? We said that octane is similar in nature to gasoline and dodecane is similar in structure to diesel. Well, what the difference is, it's a change in fuel composition. because gasoline is pumped out of the ground, it's not a pure substance. Octane, let's say, is a pure substance. It has 8 carbons and 18 hydrogens, and we know that. But gasoline has been compressed down from fossilized animals for over millions of years, and so its chemical structure is very diverse. And just to highlight this is the information I got off a material safety data sheet for gasoline, which has an analysis of gasoline, and these are the kind of ranges. So all these different chemicals or substances were present in gasoline and varying by large amounts, by plus or minus 30% kind of thing. So you've got toluene, xylene, pentane, butane, etc. So this is why it's really hard to kind of get an accurate stoichiometric air-to-fuel ratio when your substance is kind of varying so much. I mean, they do try and keep it within limits, but that's why it's different to octane. Okay, so far we've only been considering the exact amount of air that has to be reacted with the fuel. So on the previous slide, or a few slides back, we used methane, and we said we needed 2 lots of oxygen to combust with that methane to give us the exact products. But in practice, the mixture may be poorly mixed, or we might want to run it, might not be putting in enough fuel, so it's fuel lean or air rich, you could say, too much air. Or we might have a fuel rich mixture, or air lean, so we don't have enough air to get that perfect stoichiometric combustion. And a way of measuring this is by the equivalence ratio, and there's 2 of these which I'm going to present to you. The first is the fuel to air equivalence ratio. So what it is it's the fuel to air ratio that you actually have in your mixture that you're looking at, divided by the fuel to air ratio for your stoichiometric mixture. But the other way that you can say that is, it can be expressed as the air to fuel equivalence ratio. And so this is what you're probably more used to. This is represented by lambda, and it's basically 1 over the equivalence ratio, 1 over the fuel to air, 1 over the fuel to air equivalence ratio. And so what you have for this one is it's the air to fuel ratio that you actually have divided by the air to fuel ratio that you have for your stoichiometric. Now you might see either in the literature. This tends to be more used in gas turbines, but lambda tends to be more used in the automotive industry, so you'll probably see this one, but you should be very clear about which one you're talking about, because they are completely different. And this table kind of highlights it really. So for stoichiometric, it doesn't matter whether you're looking at lambda or not, the answer is 1. But here, for a fuel lean mixture, so fuel lean, so you've got more air than fuel, so this gives you a bigger number, lambda is greater than 1. And whereas if you've got a fuel rich mixture, then lambda is less than 1. But if you consider in the fuel to air equivalence ratio, then it's the other way around. So you need to be very clear about which one you're talking about. This plot shows the variation of flame speed and how that changes with lambda. It also shows temperature as well. So we can see here lambda of 1, if you remember, that's our stoichiometric ratio there, and if we have a lambda less than 1, it's fuel rich, and if we have a lambda greater than 1, then it's fuel lean. You can see that the flame speed and temperature have the same curve. You kind of have this sort of parabolic shape where you've got a peak flame temperature and a peak flame speed. Now, this is important in terms of combustion, because in terms of an engine, if we're trying to extract the maximum amount of power from our engine, this is where we want to be. This is going to give us, let's say, the maximum temperature, so it's going to heat up our gas and means we can extract the work from it, and also the maximum flame speed as well. So we're going to, thinking back to the 3 T's, that minimises the residence time we need, because we can completely combust all the fuel within the chamber. So to say, the flame temperature is linked to the flame speed. Makes sense that they go hand in hand together. And you also notice that the peak flame speed occurs and temperature occurs a slightly rich condition. I think this is because you need just that little extra fuel. So as you got increase in the amount of fuel, so you're going rich, you're increasing the amount of heat that's in the system because you put in more fuel in, so there's more energy there. But because you're reducing the amount of air, more heat is going in to heat up, more energy is going in to heat up and decompose fuel, which you're not actually going to burn. But one drops away quicker than the other, so that's why the peak is slightly rich. And you also notice that this doesn't, this comes down. If you were to extrapolate this curve, you'd end up with zero velocity. Likewise on this side. So that suggests that there are mixture ratios where you're going to have zero flame speed and zero temperature. And that's correct, because what that is the flammability limits. So a mixture of fuel and oxygen is only combustible if the ratios are within a particular range, and this is called the flammability range. And every fuel has its own particular flammable range between the lower flammability limit and the upper flammability limit. And here's the flammability limits plotted for some common fuels. We've got methane, propane, petrol, carbon monoxide and hydrogen. And this is percent along the bottom. So methane is combustible between about 5% and 15%, and propane is between 2% and 10%. Now this makes sense when you think about it. If you've got no fuel, so 0% fuel, you've got 100% air, it's not going to combust. We've only got air. Likewise, if you have 100% fuel, you have no air, so it can't combust. So it seems intuitive that if you start working in from both ends, you're eventually going to reach a point where you've either got enough fuel to initiate combustion, or you've got enough air to initiate combustion. So these if you think about it, these flammability limits make sense. There's one for petrol as well, but the really scary one is look at the wide range of flammability limits that you need for hydrogen. Okay, I've put this one up. I'm not going to talk about it in detail or expect anyone to remember it, but I put it up just to highlight that the combustion chemistry is complex. And what this is a reaction scheme for the combustion of methane. So up to now we've been writing methane, which is that one there, gives us CO2, which is that one there, and some water. But to get from there to there via, you can see that the green is the path that you want to take. So you're forming CH3, all these formaldehydes, carbon monoxide to eventually get to CO2. That's the way that you want to go. But the reaction could go any of these ways that it chooses. And all these products are being generated simultaneously, during the combustion process. So it's very, as I say, it is very complex when you look at all these steps and how you actually get from methane to carbon dioxide. So therefore, it's not really surprising that we do end up with some unwanted products. So emissions that we didn't really think that we wanted. So that's what I'm going to talk about next, is the emissions from combustion. So, as I just said, we rarely get complete combustion, and we often get a range of unwanted emissions. The common ones are, well, the only ones you get are carbon monoxide. This is toxic to humans. You've probably heard about carbon monoxide. You might even have a carbon monoxide alarm in your home next to your boiler, because there's been a few deaths linked to poorly maintained boilers. Unburnt hydrocarbons. So basically, the carbon monoxide is kind of, you haven't got enough air, and this is, just really haven't combined any of it with the air. So you get unburnt hydrocarbons. So some of the methane can go through, CH3 or CH4, whatever, and this can form ground level ozone, which is harmful to health. Particulate matter. This is different to unburnt hydrocarbons, and this is basically soot, but it's called particulate matter, or PM. You might have seen that before. And this is small particles of just carbon that can penetrate the lungs, even the bloodstream, causing harmful effects. And the next one is nitrous oxides, or NOx. It's normally written as NOx because it can either be NO by itself or NO2. Now, nitrogen oxides, or NOx, cause or exacerbate a number of health conditions, such as inflammation to the lungs, and also they have an environmental impact, as do most of the others. They contribute to acid rain. But how are they formed? So we're going to talk about that next. Okay, so carbon monoxide. Carbon monoxide is formed due to the incomplete combustion in the mixture. So if we got too much fuel, it's fuel rich, or not enough oxygen, it's fuel lean, then we're not going to get complete combustion of our hydrocarbon into CO2, because we haven't got enough oxygen to do it, basically. Unburnt hydrocarbons are formed when the fuel isn't properly burnt in the flame front. So good example of this is if fuels end up on the line of the cylinder or on the piston crown, then because they're not vaporized, it's harder for them to combust with the air, because the temperature goes into vaporizing them. So you end up with just hydrocarbons going through the vaporized hydrocarbons going through the system, and not the combustion products. Particulate matter. Now, this is formed due to incomplete combustion again, and it's just particulate matter is just carbon, so it's a hydrocarbon where all the hydrogen has been removed. Its exact formation is still unknown and kind of up for debate, but essentially it's formed by the nucleation of carbon molecules. So you have something, one bit of carbon, and then more carbon sticks to it, till eventually you get some particulate matter, which is a whole bunch of carbon, which is then exhausted out. And the last product is nitrogen oxides, or NOx. Now, this can be formed in three ways. There's thermal NOx, fuel NOx, and prompt NOx. Now, thermal NOx is nitrogen oxides that are formed due to high temperature oxidation of the nitrogen in the combustion air. So, thinking back a few slides, we showed that our hydrocarbon plus oxygen plus the nitrogen that's in the air only gives us nitrogen at the end, and nitrogen doesn't take part in the reaction. But unfortunately, that's not true, and at high temperatures in the combustion front, that nitrogen base can break down, react with the oxygen, giving us NOx. And there's a few number of ways you can do it here. So you kind of got this kind of self-filling thing. So you've got nitrogen plus oxygen gives us NO and nitrogen, and then that N will react with some oxygen to give us NO plus O. And you also have some hydroxyl radicals floating around, which can also produce NO. So it can be done in a number of ways, but the important thing is that they all need heat. So it's high temperature thermal NOx. That's how those ones are formed. Fuel NOx, well, that's fairly self-explanatory. Nitrogen. These are nitrogen oxides that are formed by nitrogen carrying fuels. So if you have nitrogen in your fuel, then that will react with the oxygen in the air, producing fuel NOx. And the last one is prompt NOx. Now this is kind of the usual term for NOx that are formed by processes other than those above. It's almost like a miscellaneous one. But one example is the nitrogen in the air that reacts with the radicals such as carbon, CH and CH2, etc. So it's not formed by temperature, or it doesn't come from the fuel, but it's formed by these other free radicals. Okay, so how do these emissions change with equivalence ratio, or lambda? Well, on this plot I've got going to plot the comparative volume in the exhaust versus lambda. Remember, if this is lambda's 1, so this is stoichiometric. If we go to the left, it's fuel rich, and if we go to the right, it's fuel lean. Okay, so CO. So as you'd expect, if we start to go lean, fuel lean, then the carbon, or the hydrocarbon, is likely to react with the air, giving you not very much CO. If you come fuel rich, then you get incomplete combustion. So, as we talked about on the previous slide, so you get increased levels of CO due to the incomplete combustion. Whereas fuel lean, you do get complete combustion. NOx. So this kind of gives kind of parabolic shape, and because NOx can be formed in 3 ways, remember, but primarily it's the high temperature which gives us the NOx. So that's why, if you remember a few slides back, we showed the variation of temperature with lambda, and the temperature peaked around stoichiometric value lambda of 1, but here you notice it's actually on the lean side rather than on the rich side, and the reason for that is because here on the lean side you have excess air. So here the peak temperature is on just about here, but here it's still hot enough to produce NOx, but because you have excess air, because it's lean, that's why your peak NOx is on that side. This is unburned hydrocarbons, so as you'd expect, you have near complete combustion stoichiometric ratio of 1, and then it increases as you decrease air to fuel ratio, or increase it as well. And this is down to a range of reasons, either excess fuel, or you're losing temperature in the combustion process, and therefore you're not breaking down the fuel, so you're increasing your hydrocarbons as well. So those are the main emissions. I've also just put on here, I'm just going to plot fuel consumption, so you can see that if you just go slightly lean, you get better fuel consumption, because that's kind of linked in to you're getting complete combustion of your fuel, so it's giving you better because you've got slightly excess air. But because of the peak flame temperature, your power, you get peak power at just slightly rich conditions. So you want to go slightly rich for peak power, slightly lean for excess air for better fuel consumption. Okay, so in terms of those emissions, the EU have set emission standards on carbon monoxide, nitrogen oxides and hydrocarbons, and particulate matter as well. And this graph shows how they've come down over the years. And you may have heard of the so-called Euro standards. So these are Euro standard tests that set the limits for the acceptable levels of emissions on vehicles sold in Europe. And they're the so-called Euro 1, 2, 3, 4, 5, 6, etc. So started in 1992, we're up to Euro 6 now in 2014. And you can see how for as each Euro standards come in, the allowable amount of particulates, normally expressed in grams per kilometre, has been driven down quite drastically. The Euro standards are becoming increasingly stringent, and consequently we need to develop new technology all the time to meet the standards, and that's what we're going to talk about next, ways that we can reduce these emissions so that the future vehicles can meet the future standards. One of the most common ways, and you've probably heard this one, is the catalytic converter. And so what this does is it takes the products, and you can either have a two-way, which only converts carbon monoxide and which controls carbon monoxide and hydrocarbon emissions, or a three-way where it will also deal with the NOx as well. So what they do is they normally contain precious metals on a substrate, and as I say, because of the word catalytic, the precious metals aren't involved in reactions, but rather act as a catalyst. And so what it does is it does three things. So it will take your NOx and it will combine that with excess oxygen in the exhaust, giving you nitrogen. It will take the CO and it will completely oxidize that to carbon dioxide. And it will also take your hydrocarbon, whatever that may be, in this instance an alkane, and combine that with oxygen, giving you CO2 and water. So as I was saying, it's doing three things. Three-way does the carbon monoxide, hydrocarbons and NOx, and two-way does just carbon monoxide and hydrocarbons. However, two- and three-way catalytic converters have to operate in a narrow band of equivalence ratios. That means that three-way catalytic converters are unsuitable for diesel engines because of the the narrow operational band. Diesel engines typically run with excess air, so they are outside of these bands. So therefore, diesel engines just run with a two-way catalyst, or a so-called diesel oxidation catalyst. So the NOx has to be done in another way. And one technology that's becoming more and more, started off in heavy and diesels, and now making it into the passenger market, is what's called an SCR, or selective catalytic reduction device. And this is used to treat the NOx. So the SCR uses aqueous urea to reduce the NOx to nitrogen, water and carbon dioxide. So this is a formula for it. So you have nitrogen oxide plus your urea solution plus oxygen gives you your products, your nitrogen, water and carbon dioxide. As I say, this is actually sprayed into the exhaust, and you might have seen some of the diesels on the road, or AdBlue at the pumps. AdBlue is just a trade name for the commercially available aqueous urea solution. So it's a separate tank that's actually carried with the vehicle and sprayed into the exhaust. however, we got rid of our CO, HC, hydrocarbons and our NOx. We also need to get rid of the particulate matters. And if you remember from the first lecture I gave, the video that showed how sooty the combustion of diesel was compared to gasoline. So modern diesels now have been fitted with a particulate filter, which is used to remove the particulate matter from the exhaust. And this is nothing really more than a glorified sieve or filter. It just catches the particulate matter. You can quite often regenerative diesel particulate filters are used, where once the pressure drop across the particulate filter reaches a set value, it will then run the engine hot, burn off the soot again with excess air, and regenerate the filter. So essentially, this is what your exhaust system looks like now for a diesel. So you've got your engine giving you particulate matter, carbon monoxide, hydrocarbons and NOx. Use your diesel oxidation catalyst to oxidize your carbon monoxide and hydrocarbons to water. Your diesel particulate filter catches your PMs, and you, as I say, literally spray urea into the exhaust, and that reacts on the SCR, giving you nitrogen, carbon dioxide and water. One other way that can be used to reduce NOx emissions as opposed to the SCR is EGR, or exhaust gas recirculation. What EGR does is it basically recirculates a proportion of the gas back into the cylinder. So all the exhaust products have gone out, they literally come back into the cylinder. That can be done kind of externally or internally. So you can externally, you've physically got a pipe which is connects the exhaust manifold to the inlet manifold, or internally you can use the valve timings to achieve that. Anyway, the proportion of the exhaust gases, what it does is it dilutes the air coming into the cylinder. So instead of having this whole new cylinder of fresh charge, you've got a percentage of exhaust gas, and because it's already combusted and oxidized, it can't be combusted again. So what it does is, when you put in your air and you add some more fuel and you combust it, not only does it kind of displace that charge, but it also absorbs the heat from the combustion process, reducing the combustion temperature, which will lower flame speed, but more importantly, it reduces NOx. And it's a lower temperature that reduces lower NOx. And as I said, there's two ways it can be achieved: external, where the exhaust gases are piped from the exhaust manifold to the inlet, or internal, where there's large valve overlap to trap exhaust gases in the cylinder. Okay, that concludes this lecture on combustion. Again, if you have any comments, queries, or want to see me about anything, my contact details are here, and thank you for listening.